Hello, everyone. I think we can start. Hopefully you can hear me. And well, good afternoon, everyone, and welcome to this thematic workshop on machine learning and big data in physics. This workshop has been organized by the International Physicists Network, which is a non-profit organization actively promoting the role of young researchers in physics. To check out the activities of this association and to get involved, please visit the social media channels or the website. We will post probably in the chat all the references. By far, however, by far the most representative activity of this association has been the organization of the Young Researcher Meeting, which is a yearly conference which has been going on since 2009, and every year has been held in different universities and research institutes across Italy, with the exception of last year. I mean, in 2020, we couldn't do the conference. I mean, the conference had to be cancelled for reasons that are obvious to all of you. The conference was supposed to happen in Trento, in fact. Not being sure when we will be able to organize again a meeting, a conference with people gathering in person, together with the colleagues of the University of Trento and of the Bruno Kessler Foundation, we decided to organize this online event. I mean, online events nowadays are the normality. However, for us, for the Young Researcher Meeting, this is a pilot event, and we really hope to do more of this. So if anyone that is listening would like to join in the organization on next events and get involved, as I was mentioning, please do get in contact through various channels. For example, in the chat, you should find now the website address. So as I was mentioning, this is a pilot event for us. It will be devoted to machine learning and big data in physics. So quite a treat, as this theme is quite topical. And as you probably have seen, the program will feature 3 invited talks by young researchers in physics that will span different branches, that will pertain different branches of physics. At the end of these 3 talks, we will have a panel discussion with all the speakers. And our guide for the afternoon is Luca Tubbiana. Luca Tubbiana, who should be probably already connected, is a Rita Levi Montalcini Research Fellow, and he works in biophysics at the University of Trento, and among other things, he teaches, hi Luca, he teaches computational biophysics and data science for physicists. Also, he has had a previous experience as a data scientist in a major financial company in Germany, if I'm not mistaken. So we really thought it would have been brilliant to have him as a guide for this afternoon, and we are really happy to have Luca with us. So before leaving the word to Luca, just 2 technical notes. First of all, the workshop is recorded. So the video of this workshop will be available on our YouTube channel, on the Young Researcher Meeting YouTube channel. So check it out later. And second, questions. So if you have questions, you can ask them throughout the entire workshop using the Q&A tool. So writing the questions in the Q&A tool, or using the raise hand feature that Zoom has. So you can raise your hand if you want to speak up and ask your question directly. At the end of each talk, Luca will convey questions that have been written in the Q&A tool, or we'll give you the word, we'll give you the mic. If not all the questions can be asked after each talk, they will be addressed at the end of the meeting during the panel discussion, so don't miss it. So Luca, I leave you the floor. Thanks.
Thank you. So thank you, Marina. Thank you very much for having me as a chair of this wonderful event. I had the occasion to discuss a bit already with the speakers a few days ago, and I'm sure I myself will learn a lot from their talks, which are very, very interesting. So, well, I welcome everybody, first of all. And today you will hear, as Marina has already told you everything, but just to repeat, you will hear about 3 different topics in physics, where machine learning methods and big data are applied. So the first talk will introduce you to applications to high energy physics in a satellite detector. The second one will move to biophysics and medical imaging, also with a lot of interesting applications to neuroimaging, and therefore to medicine. And the third one will bring us to cosmology and research which goes into the direction of answering how our universe formed. So as you can see already from the choice of topics, these methods which originated from computational science now find very, very broad applications at the most fundamental level of physics to the applications, and then also to way more applied endeavor, which are not covered here. Well, without further ado, I will like to leave the floor to the first speaker of today, which is Francesco Maria Follega. So Francesco is a researcher at the University of Trento and the Trento Institute for Fundamental Physics and Applications, TIFPA. And he got his PhD from the University of Rome La Sapienza in energy physics. And since his PhD, he specialized, dedicated his research to develop a new advanced methodology to analyze big data typical for high energy physics machines. And his most recent work is dedicated to the application of machine learning methods for a detector which will end up in the Chinese seismoelectromagnetic satellite detector for the Lima 2 experiment, born out of a collaboration between Italy and China to try to measure, as Francesco will explain, with satellite the aftershocks of earthquakes. This is quite a daunting task, and Francesco will tell us more about how machine learning can help with that. So, Francesco, please.
Here I am. Thank you. Thank you for the introduction, Luca.
Oh, one technical note. You have 25 minutes. I set an alarm for 24. So when it rings, you have 1 minute to finish. Then there are 5 minutes of questions.
Thank you. Thank you. Let me share my screen. Can you see it?
Yes.
Can you see it when I go full screen?
Yes.
And you see also when I change the slides, right?
Mm-hmm.
Perfect. Okay. So thank you very much, Luca, for the introduction, and thank you for all the attendees of this webinar, actually. I'm very thankful to have the opportunity to present part of my work, which consists in the deep learning-based event reconstruction for this high energy detector called Lima 2 HPD01. So the seminar will be structured in 3 sections. The first one about an overview of application of deep learning in particle physics. a second one with a zoom in inside the Lima 2 HAPD case, and a final one with the prospects of this detector and of this deep learning application to the event reconstruction of this detector. So let's start with the introduction. First of all, some basics concept, which will help us to go through the talk. What is a particle physics detector? It is a block of instrumented material divided in sub-detectors. You have a tracker, which is a detector with, that reconstructs the arrival direction of the incoming particles. Then you have a trigger, which is a part of the detector that fires every time a particle enters in the core of the detector. And you have a big block here in orange, which is the calorimeter, where the particle enters and releases all its energy. So what is an event in high energy physics or particle physics? Is when a particle interacts with your detector, and at the end it dies inside the detector. In order to measure this particle and its characteristics, you have to destroy it at the end. So here you have two examples. The interaction of an electron with the detector. You see that the electron enters inside the detector, it leaves a signal inside the tracker, and then the energy deposits a steady amount of energy over the calorimeter. Instead, the proton is different because it is actually not an elementary particle. It's made of hadrons. And therefore, it makes a different interaction. And it starts to get in the detector, then it starts to leave more and more energy, and after a peak, it dies. This will be a feature which I will take again in the talk. Therefore, from the amount and the shape of the signal deposited by the particle inside the detector, you can reconstruct important quantities concerning the event, which is the interaction. Like, for example, the angle of the incoming particle, the kinetic energy of this particle, and the identity, if it was an electron or a proton. Deep learning algorithms nowadays play a key role in the event reconstruction of the most modern particle physics experiments. They perform particle identification, the identification of the nature of the particle. They perform tracking or energy reconstruction. They are used in parallel or as a substitute of the standard event reconstruction because they offer offer many advantages, and they show a few drawbacks. One of the most important advantages is that they account for all the correlation between the input variables you feed these algorithms. And sometimes you know that these correlations are hidden or not easy to model at all. They can also exploit for detector asymmetries or data inhomogeneities and compensate for them. But they have a strong limit. This strong limit is that they rely on the training data set. So on the data which you show to the model and that the model learns how to model. These data have to be really representative of your population. If not, you introduce a bias, which will be then showed by the machine once you evaluate on a different data set. The first event I want to bring to you is the big work identification in ATLAS. ATLAS is one of the most important particle detector and experiments ever built in the history of particle physics. It was one of the two experiments which discovered the Higgs boson in 2012. And here you have an event in which two protons collide here in the center, and they produce a lot of signal inside the detector. Then, if there was an Higgs that it was produced, it most probably decay in a couple of big quarks. And these big quarks need to be identified to be correlated to the Higgs. This is one of the most important tasks in the ATLAS detector, the ATLAS experiment, to identify which signals belong to big quarks. And it is actually performed by a set of different algorithms. Here you have a show of the performance of these algorithms. On the x-axis, you have the efficiency, the probability to identify a big quark when there was a big quark. And on the y-axis, you have the power to reject background. So the power to reject fake big quarks. And you can imagine that you want that the area below the cube is as much as higher as possible, as much higher as possible. And here you have three different sets of algorithms. Low-level taggers, which are algorithms based on standard event reconstruction. So they are cut-based algorithms, which are the one clustered here. And then there are two other algorithms, the blue and the purple, which are based respectively on machine learning algorithms, like the decision trees, and deep learning algorithms, which are, in this case, fully connected neural networks. And you can see how they outperform the other algorithms in both the plots here. Then there is also application of deep learning to the tracking onto the energy reconstruction, which are two important tasks in particle physics. For example, in 2018, CERN organized a challenge, challenging the participants to develop a fast and accurate method to track particles in dense environments with the help of deep learning. So you have a data set that was like this, and you have to gather the signals, the hits inside the detector module in order to form tracks. One of the proposed solutions for example, by my working group was to cluster the hits with a DB-scan algorithm, which is a machine learning clustering algorithm, to cluster the hits on the same detector module and then extend the track from the innermost to the outermost module with the help of a fully connected neural networks. Another application was the energy reconstruction of in the calorimeter with the help of convolutional neural networks. Here you have an image which represents the amount of energy deposited and the shape of the deposit inside the calorimeter. And you can give this image to a series of these images to a convolutional neural network to reconstruct the energy and the direction of the particle inside the calorimeter. So let's now zoom in the case of application I wanted to talk to you about today. Limadu HPT01 is an Italian detector. Actually, a great contribution was made by the University of Trento to this detector. And it's the high energy particle detector of the CEF mission. CEF is a satellite that was launched in the 2nd of February 2018 and is now orbiting around the Earth. And this mission aims to observe correlation between seismic events and particle bursts or anomalous particle fluxes in the ionosphere. As you see here, this detector is still similar to the sketch I showed you before. It has a tracker, a trigger, a calorimeter made of these planes and of these cubes at the end. So what we did with, what is the scientific objective of this mission? The scientific objective is this earthquake correlation with particle bursts in the ionosphere or magnetosphere. So when an earthquake takes place, there is a lot of energy that accumulates in the earthquake preparation area. This energy is then propagated towards the outside via electromagnetic waves at low frequency. These electromagnetic waves interact with the particle trapped in the Van Allen belt, and they make this particle precipitate, and this particle can be intercepted by a detector which is orbiting in that region. And this is exactly what CEF is doing right now. There were already some indication of this correlation between earthquakes and particle bursts that were measured by other experiments. You see here that there is a peak in the time difference between the earthquake and the particle burst around from 2 to 4 hours around the earthquake. But this mission aims to reinforce the statistical significance of the measurement done before. So at some point in this experiment, we decided that to exploit really every information of the detector, a deep learning approach was worthy to try. Therefore, we constructed a deep learning reconstruction chain, which is depicted on the left, made of the following elements: a fully connected neural network which discriminates between electrons and protons, and two fully connected neural networks, one trained on protons and one trained on electrons, that reconstructs the energy, the arrival direction of the incoming protons or electrons based on the signals collected by the detector. The architecture of these neural networks is rather simple and is depicted on the right. You have 6 layers, 4 hidden layers. The peculiarity of this architecture is that the layers are made by nodes, and each node is fully connected with the nodes before and after. And we use also a regularization to prevent overfitting, and we use dropouts between the hidden layers in order to randomize a fraction of the nodes. Then we needed a trained data set to train these networks. And then we decided to do this with a Monte Carlo simulation. So we simulated protons and electrons interacting with the detector and the signals of this interaction, which is left in the detector. And we use this signal, the shape and the amount, to reconstruct the angle of the incoming particle and also the energy of the incoming particle. The training procedure, we decided to train the fully connected neural networks independently in order to keep the prediction of particle amplification and the kinetic quantity uncorrelated as much as possible. We had a pre-processing step in order to scale the input signals in the same range. We trained with cross-validation, and we use a statistical independent test sample to assess the fully connected neural network performance. And we optimize the parameters with a grid search. And here you see the behavior of the loss for the fully connected neural network, which separates between proton and electrons, which was a binary cross entropy, and the behavior of the loss for the reconstruction of the kinetic quantity, which was a regression problem, and which was a mid-square error loss. Here you have an example of the performance we have for the identification, the separation between protons and electrons. And here you see that actually, in order to compare with the previous model, here I quote you the accuracy, which is 96% on this test sample, and on the same sample, which is 10% higher than what we get with the standard event reconstruction. The efficiency and the mistake rate are depicted on the left and on the right, and they are the same, the two faces of the same medal. Then let's start with the description of the performance for the energy reconstruction. Here you have a scatter plot of the energy generated with the Monte Carlo against the energy predicted by the neural network for protons. And here you see that everything is well aligned on the bisector. That means that we predict what we generated with the Monte Carlo, and this is a good news. Another thing that you can notice is that above this vertical red line, protons are not contained anymore in the detector. It means that the energy should not be reconstructed, because you need to suck all the energy of the particle to contain the particle inside the detector to determine precisely the energy. Here, you see that the network is able to reconstruct the energy above this containment threshold, and that is because it exploits the shape of the signal deposited inside the detector, and it actually exploits the rising path of the charge deposited for protons, and also the position of the Bragg peak inside the detector. This is the way in which we can extend the reconstruction of the energy also for not contained particles. We have also the angular reconstruction, which is a challenging task for us. Indeed, we have to use all the information in the detector and also the position and the shapes of the signals deposited inside the detector to reconstruct a direction. The metric we decided to use in order to quote the difference between the direction generated with the Monte Carlo, which is the green one, and the one reconstructed by the network, is the angular difference between these two vectors in the tridimensional space. The less the smaller is this angle, the better are the performance. And here you see that using more and more information in the training of the neural network, you end up with a distribution which has a peak of 3.5 degrees, at 3.5 degrees, which is the error we have in the angular reconstruction. Now let's start with the future steps of this work. So ASIAN, Chinese National Space Agency, agreed for a new Italian participation to the XS mission, which is the XS-02 mission. This collaboration actually aims to reconstruct, to build a space observatory made by many satellites, which constantly observe the Earth from the space. And the activity started to the design and construction of a brand new high energy particle detector, which I cannot show right here because it's internal and the design is also ongoing. And the success of the deep learning event reconstruction of the first detector pushed the collaboration towards a new version of the detector with a deep learning event reconstruction chain. Here you have a sketch of this new event reconstruction based on deep learning. We now plan to organize the information separately for the tracker, which will be a pixel tracker. So we will have images from the tracker, which represents the position of the hits in the detector. And we will probably end up to use a convolutional neural network to analyze this input signal on the 3 tracker layers. We will do approximately something very similar to what we did for the calorimeter. Then we decide to concatenate all the information and to predict all the important variables all in once, because we noticed that the angular variables and the energy and the identity of the particle are very correlated. Therefore, predicting them at the same step will help the algorithm to learn this correlation. The important thing that I want to stress is that now also the tests of the apparatus are somehow oriented toward this deep learning event reconstruction. Indeed, the number of tests and the granularity of these tests is now grown a lot, because we know that covering with real data, with tests on the apparatus, so real data, non-simulated data, covering all the possible phase space in energy, in particle type, and also in angle, will help us to tune the event reconstruction based on deep learning on real data. There are many different strategies to tune this algorithm on real data, but the tuning is fundamental because we know that the Monte Carlo is not a perfect reconstruction of what we have in the detector, because they are 2 different objects. And therefore, every small difference between data and Monte Carlo will bias the prediction of the network on the flight data, on the real data. Therefore, we are trying to find a way to transfer the knowledge we have on Monte Carlo to real data. And there are many techniques to perform this domain adaptation. The first one will be to train on a mixture of the Monte Carlo data and on the real data. The second one will be train the network on Monte Carlo, then reset the last layers or a fraction of the nodes, and then tune these nodes on the real data from the test beams. Or we can use a technique which we are studying right now, which is already used in high energy physics experiments, which is this domain adversarial neural network, which is an additional part in your network, which tries to minimize the sensitivity of your reconstruction to the difference between data and Monte Carlo, to the difference between these 2 domains, really similar but not equivalent. It will therefore make the network learn how to use features that that are not discriminative between the 2 domains. Or we can use an hybrid of the above ones. And this brings to my summary. We have an overview of the deep learning application to high energy physics. I've shown you the DIMA2 HPT event reconstruction, which is new and pioneering for this kind of environment, which is maybe one of the last field of physics which is now trying to integrate these deep learning and machine learning techniques inside the standard analysis. And I've shown you a glance at the performance, which are now used by the collaboration. And I also shown you the prospects for the all-in-one deep learning event reconstruction for the new detector, plus the plan on tuning on real data. And that's all from my side. Thank you for the attention and for the introduction.
Okay. Thank you very much, Francesco. So you were actually 3 minutes short. So there is more time for questions if anyone wants to ask some questions. And just to note it, for the next 2 talks, you can write the questions in the chat even during the talk, or even better in the Q&A, so that I can then refer them or just give the word to whoever asked the question at this time when the talk's end. So anyone? Raise your hands in case. I don't see any hand raised, but perhaps that was because of the chat. So let me. So I also asked the other panelists, because I cannot see the, okay, I see now a Q&A. I cannot see hands which are raised. Okay, Francesco Nozzoli, well, wants to ask a question. Perhaps he can ask himself if we give him the mic. There's some difficulty. So the question is for Francesco, if you have some slides to explain a few deep learning methods.
Okay.
Some introductory slides.
Okay, I see now. I heard Francesco speaking right now. Okay. Hi, Francesco.
Hi. Yes, because you explain very good your use of deep learning. I don't know if all the public is expert of this technique. Can you spend some basic about them?
Yeah, I have actually a slide of on the algorithm which I used maybe more extensively, which is this fully connected neural network. And as I've tried to explain you before, but very quickly, because I thought to be late actually, and I tried to rush. There is an algorithm which is called fully connected neural network. So here you have a network which takes as input a multidimensional vector. And this network is made by neurons, or also called nodes. And this neuron is actually constituted of a linear part, which is a set of weights plus a bias term, which multiplies your vector, your input vector. Sorry, and then an activation function is applied to this product, which introduces nonlinearity inside the problem. I actually use a rectified linear unit to activate my neurons. And here you make these numbers flow over all the network. And you're trying to, the learning procedure is actually made by minimizing a scalar called the loss function, which is for, in this example, a mean square error, which is the difference between the label, which are the ground truth, and the prediction of your network squared, and the mean value of this. you try to minimize this color, which is actually a function of the node, a function of the weight if you use the chain rule to backpropagate. And here you have a sketch in which you express this loss function as a function of a configuration of the weights, which is the configuration of the weights for all the nodes in this network. And you try to move these weights, to adjust these weights in order to minimize the scalar and to flow towards a global minimum, which is where the loss stops to decrease. And here, actually, if you reach a global minimum, it means that the model has learned what it could with this kind of architecture. This is a trivial explanation of deep learning of a fully connected neural network.
Thank you very much.
Okay, there are a few more questions. I will go through the firsts, and then the others will remain for the later discussion session. Okay, so in case we don't have time to cover all now, don't be afraid, there will be time later. So the first one from an anonymous attendee. How does, sorry, since you're anonymous, I cannot give you the word. How does the application of this machine learning help deal with the noise in the detector used in avalanche detectors in photonics integrated design?
I mean, this is actually a very good question. I don't think I have an answer in my backup slides, but maybe we can discuss about it. It will be a long discussion, actually, because the person who asked the question maybe knows that in this kind of detectors, you actually generate signals toward the photon generation in the scintillator planes, and then you collect these photons with photomultiplier tubes, which then convert the signal to electric signal that you can read with your electronics. And actually, I never heard of experiments which, but it will be also my ignorance to speak. I never heard about detector who use fully connected neural machine learning to lower this noise, but it will be a very good application now also in this case. Actually, we do not do a special treatment to reduce the noise in our detector, but it is a great suggestion. We already think about something like this for the future detector, but I mean, concerning what I've shown you here, there is no application of machine learning in this direction.
Okay, I think the continuation of this might perhaps be a good topic for the discussion, as you said. There is time for sure for another question, maybe two, depends on the, so we started 10 minutes late, depends if we want to recover the next question from Alessandro Bitetto. So perhaps he wants to ask himself.
Yes, good morning. So my question was about the size of the data set you used. Probably I skipped, I missed the information during the talk. How big is the data set?
So I didn't mention it expressly, but I wrote it written in a slide. I actually used a simulation which was already prepared by the rest of collaboration, which consisted in 5 million of events for protons and 5 million on events for electrons, simulated for each possible direction coming towards the detector, and with a flat spectrum of kinetic energy, which somehow represents what we expect in flight. And the data set instead from the Kaggle challenge was a different data set, nothing to do with the Lima 2 HAPD01 data set. It is actually available on Kaggle. And I think it will account for, let's say, maybe thousands of events, 10,000 events, where each event is something like that. In each event, you have like 200 tracks or maybe more. So here the multiplicity of the event is given by the track. So you have 2 million tracks in this data set. But they are two different data sets. One was produced by CERN and the other one was produced by our collaboration.
Okay, thank you.
Okay. Since we are now 5 minutes late, perhaps, or let's keep the remaining 2 questions for the discussion time. So I ask the Claudia Borredon and Lorenzo Sedita, who asked this question, to remain here to the discussion, the panel discussion. And I thank you again, Francesco, for his presentation. And we can proceed with the next speaker, who is Marco Palombo. There he is. Here we change the topic quite a bit, and we go from high energy physics to biophysics with some very interesting potential applications to medicine. So Marco is, I forgot the title, I'm sorry. So is a biophysicist who also graduated from Rome La Sapienza, and who is currently working since 2016 at UCL in London as a senior research associate, and who has been awarded the prestigious UK RI Future Leader Fellowship thanks to his proposal to develop innovative diagnostic imaging tools based on magnetic resonance and machine learning. And in particular, for what I've seen from some articles of his, he has this very interesting application to diffusion MRI, which is a very nice technique that lets you see, let's say, how water can diffuse in microstructures, and from that, understand what are the microstructures. And these kind of techniques are the one used, for example, to map the connectome of white matter in the brain. So very exciting applications as well. So without waiting any further, I leave the word to Marco.
Thank you very much for the nice introduction, Luca. Can you see the slides and the pointer?
Yes.
Excellent. And can you hear me well, right?
Yes.
Okay, thanks a lot. You have done basically the introduction slide of the work. So as Luca said, I will showcase some application of machine learning to this specific task of trying to extract quantitative information of the brain microstructure non-invasively using a technique, a specific branch of the MRI technique, which is called diffusion-weighted MRI. And it's widely used in all the hospital, diffusion MRI as a basic technique. What we are doing at UCL is to enhance the possibilities that this technique offers to non-invasively characterize the brain microstructure. And what we want, our mission is then to resolve still open issues and questions about multiple diseases and conditions of the brain. So the outline, I will quickly introduce what is diffusion MRI and how we link the signal that we measure with the MRI scanner to the actual tissue microstructure and how machine learning can help in this. And then I will present a few examples from my direct work on using computational modeling coupled with machine learning for this task of quantifying tissue microstructure. I will summarize with some take-home messages about machine learning in medical imaging in general. And if there is time, I will also, I would be very happy to show you some more work done from our group about super resolution of medical images. But we will see, I doubt there will be time. So I'll move quickly. So our task is to quantify tissue microstructure. What we mean with that is that we would like to access information about the cells, the individual cells. Information such as what's their shape, what is their typical sizes or characteristic length scale, what is their density, are they organized in layers or are they randomly displaced within the tissue? So these are all extremely interesting questions that have a high medical value, especially for the diagnosis of the diseases. Now, the problem is that if we take the human brain and we take an MRI, that's the resolution that we can achieve with one of the best scanners in the best hospital of a developed country. It's 1,000 micrometers, it's 1 millimeter. If we want to access directly the tissue microstructure, I mean the structure at the microscopic scale, well, we need histology or we need a specific microscopy technique. And as you may know, histology and microscopy in general cannot be performed in vivo yet. So you need to take a sample and then stain this sample ex vivo and get these nice detailed images. So we face a problem, which is a huge gap of resolution between what we can achieve with our technology non-invasively when you go inside the scanner in the hospital and what we want to measure, which is on the scale of the microscope of the micrometers. So it has been proposed already 20 years ago that a possible bridge to bridge these two scales is to use the diffusion of endogenous molecules to probe the tissue microstructure, because the diffusion in the typical time scale of an MRI experiment can cover exactly that range of scales that we need to cover. So how we can use diffusion of endogenous molecules, such as water in the tissue, to extract information on the microstructure. So I'll borrow these slides from a talk I gave last year in a conference in Montreal. That's why you see the map of Montreal. So let's assume we can label each person in this map, each person in the Palais de Congrès, we can label in red, each person at this crossing street in green, and each person in this square in purple. If we let them run randomly in space, they will perform a random walk. Okay, and random walk, it's actually what happens when molecules diffuse under the effect of thermal agitation in your body. Now, as you can see, the shape of the displacement distribution of the people take the form of the boundaries that restricts their motion. So for instance, it takes the shape of the Palais de Congrès or the crossing of the street. So that's the principle. With MRI, we cannot access all these details, but maybe we don't need that. Maybe we can just label the molecules and quantify the probability distribution of their displacement, and that's enough to get information about the size, the shape, and so on. That's exactly how diffusion MRI works. So if you take the brain again, you have different tissue types. You have white matter, which is comprised of packed axons, which are very anisotropic structures with a main direction of these fibers, in this case is along this direction. And then you have gray matter, which is a packed, highly dense tissue of cells where membranes are randomly distributed in space. This is the pattern of the water molecule displacement that we would see in each one of these, for instance, in gray matter and white matter. As you can see here, this displacement distribution is Gaussian in space, is isotropic in space, while this one is more anisotropic. So we can infer that the main direction of the membranes, in this case myelin layer around the axons that restricts water, is in this direction, while here we can perhaps get estimates of the average density considering how much the diffusion has been hindered by the cells. And we do this via MRI, and knowing that the diffusion weighted signal that we measure is the Fourier transform of the motion propagator. So what we access is not directly the displacement, but it's the probability that a molecule performs that displacement at a given time, the Fourier transform of this. And as you can see here, that's the typical signal you would measure in these three different tissues. Okay, so we understood maybe we can use diffusion MRI. However, it's difficult because the signal that we measure, this Fourier transform, kind of, due to the Fourier transform, we lose a lot of information about the underlying displacement of the molecules. And we need to reconstruct the tissue from this fairly simple and featureless signal. So to help with this, one possibility is to use biophysical modeling. So that's how it basically works. You collect a bunch of measurements, changing your diffusion weighting, which in the medical arena is called B, which is proportional to the Q vector of the Fourier space. So here you are sampling the Fourier transform of the motion propagator. And you collect some signal in each voxel, in each pixel of your image. Where if the image has multiple slices, it's a three-dimensional pixel, which is called voxel. So biophysical modeling takes place when we want to go from the signal to the microstructure. So let's assume we have what you see here in blue are axons from real axons from electron microscopy. With biophysical modeling, we say we don't care of the undulation, the beading of the axons. We assume they are negligible to they contribute in a negligible way to the signal. So we just care of the sides and the direction and the density of them. So we model them as cylinders, and we model the tissue as packed cylinders of different sizes. For this kind of model, we know closed form analytical solutions for the motion propagator. So we can come up with an analytical model and fit it to the data and extract proxy measurements of what is the axon radius associated like the cylinder radius, while the cylinder density would be proportional to the axonal density. So we can get non-invasively maps of axonal size and density of the brain of a human subject in an MRI scanner in an hospital, something that you would need a microscopy to do so. So how can machine learning help? So what I told you seems simple, but if you look at the actual pipeline and the actual processing involved, it can be quite complex. Well, machine learning can help in every single step of this. Just to summarize, it can accelerate data acquisition. So it has been shown that machine learning can help a lot when data are heavily undersampled. So you don't need to sample this Q space densely. You can just sample it much less and then use deep learning to recover what you didn't sample. For denoising, you can use machine learning techniques that are excellent to clean the signal that you measure from the noise. For super resolution, and as well as accelerate the estimation. So fitting these biophysical models is highly time consuming. If you use deep learning, it accelerates massively the fitting, or even to substitute approximate biophysical models with something which is all data driven, or perhaps more accurate, more realistic than just cylinders for axons. So if you are interested in this topic, there is this nice review I recommend you because it covers most of the application of machine learning in medical imaging. What I highlighted here is a field that is currently not highly represented by the publication, which is actually the field I'm going to work and to push forward in the future. And this field comprises exactly how we can make the biophysical models better and how we can accelerate the model fitting. So I'll show you straight away one practical problem we would like to solve. So let's take a condition of the brain like multiple sclerosis, and let's take one of its hallmark, which is demyelination of the neuronal axons. So this is a typical neuron, an healthy neuron, where you see the axon is this one, and an healthy axon is covered by myelin, which is this double layer that you can see in dark gray. During the onset, the early onset of the multiple sclerosis, axon starts losing the myelin, and progressively this lead to neuronal, to axonal loss and neuronal death. So if we can quantify this demyelination process, we can diagnose MS much earlier, and perhaps we can help the patient going through a better progression or prognosis of the disease. So one way we can do it is to label, as I told you before, we label people in the Congress, we can label with MRI the water molecules, in particular the protons of the water molecules. And we can say, okay, we have water molecules inside the axons and outside. Myelin is a lipid layer, so water cannot cross easily the myelin. So the exchange between water intra and extra-axonal should be very slow in an healthy neuron and much faster in a diseased neuron where demyelination is ongoing. The problem for this, okay, that seems a brilliant idea. However, there's a problem. If you try to solve the biophysical system of water exchanging between these two compartments, it's very challenging, and it's a topic has been tried for 20 years in the field. There is still not a proper, accurate solution that can give us an analytical model. So the idea, let's replace it with simulations, with Monte Carlo simulations of particles inside a tissue, a synthetic tissue, made of packed cylinders, where water can cross the cylinder membrane with a certain probability. At this point, we can quantify the exchange via the exchange time. So when the axons start losing the myelin, this exchange time should be short because the exchange is faster. How we can, from the simulation, map in each voxel this exchange time via machine learning. So basically, we can simulate thousands of different conditions with our Monte Carlo simulation and train a machine learning algorithm model, for instance, a random forest, to learn the mapping between the unseen measured signal and the known features of the simulated substrate. And we can get map of not only axonal volume fraction, but also exchange time. So how this works in practice, we generate thousands of different configurations to perform Monte Carlo simulation. For each of these virtual substrate, we know the features of interest, such as the size alpha of the axons, the density F, and the exchange time tau. We generate a signal. We can either use the raw signal or we extract information out of this signal via features that we know can be useful. Then we separate this data set into a training set and a test set. The training set is comprised of a coupled signal or features and the parameters that we know a priori. We feed the signal or features to the machine learning model, and we use, in training, what we do, we minimize the prediction of the parameters from the signal with the known ground truth by design. Once we trained the model, then we apply to the testing set to evaluate the performance in terms of error, accuracy, precision, and so on. Of course, you can use any model, or any machine learning model. So rather than a random forest, you can use a fully connected neural network that we have seen in the slide before explained very well, which is exactly the same architecture, fully connected layers. You give an input this multidimensional vector of signal or features, and you learn the mapping between the input and the parameters you want to estimate. And you do this voxel by voxel. So in this case, your input is a vector of signal for each of voxel in the image. A typical MRI image has 100,000 to 1,000,000 voxels. So you do this for each one of these voxels. You understand that machine learning can help making this process extremely fast. So typically, if you try to do this with any other method which is not machine learning based, regression method which is not machine learning based, it can take you a day. With machine learning, it takes you 15 seconds after you have trained the model. So this model can be deployed in the hospital, and you can get these maps on the fly. The patient has been scanned. By the time they comes out, they have already this map available. Here you can see an example of these parameters on an healthy subject, but very interestingly, applying this to multiple sclerosis patient, you can see how these two regions have a very different contrast, with the exchange time much lower in this region than this. In fact, from other exams, this patient had a demyelination ongoing in this region of the brain, while this other region was healthy. If you try the only model, which is a very approximate, rough biophysical model of exchange, you can see how you lose the sensitivity to this very important feature. Okay, the next step we have done is to validate that we are actually measuring, we are doing modeling and we are using simple simulations of cylinders. Are you actually measuring the myelin thickness, the myelin layer, when you do this kind of approach? We performed experiments in a mouse model of demyelination, intoxicating mice with cuprison, whose effect is to lose myelin in the corpus callosum, which is a white matter region in the brain here. And as you can see here, compared to the healthy mice, those intoxicated has much lower exchange time, because you can see it's much greenish rather than red. And when we correlated with electron microscopy measurements of the myelin thickness, the black ring you can see here, we found a very strong linear correlation between what we measured in vivo, non-invasively with MRI and machine learning, and what we measured ex vivo after sacrificing the same mice and performing electron microscopy. So this is very promising. Another application we have done is instead, can we actually quantify the whole brain cellular structure using the same philosophy, using the same approach? Well, first of all, we need to come up with a generative model for the brain cell that we can use for the simulation. So we have implemented this generative model that can be used for both glial cells and neuronal cells. We don't use water, we use other molecules as our labeled probe molecules where diffusion is applied. And we use exactly the same. We build a dictionary of simulated diffusion coefficient as a function of time. And then we use machine learning to predict what is the time dependence of this diffusion coefficient given a specific configuration of the cellular tissue. And here you can see what the model predicted in a continuous line, in solid line, and the dots are our measurements in two species, macaque and mouse. And you can see how in macaque we estimated 2.5 times bigger glial cells, astrocytes, compared to mouse, which is very good in line with 2.55 from histology, while for neurons we didn't measure big differences. To be more quantitative and precise, we sacrificed the mice and we performed one-to-one comparison between the predicted cellular structure from our computational model and machine learning and the measured one, and we didn't find the statistical difference. So in vivo, without invasively or using ionizing radiation, we were able to measure very important features, such as how complex is the cell, how many branches it has, how big it is, and so on and so forth. This can be very useful, for instance, for quantifying inflammation. where a specific subtype of cells called astrocytes become reactive, which means they become bigger and more complex. We applied this method, and as you can see here, what we measure with machine learning and computational modeling is very good agreement with what we measure with histology. And this is done, again, non-invasively without hurting at all the mouse. Of course, this is a preclinical study. Now we are working to push this technology and these approaches into clinics, but this takes time. One thing I would like to show you is what are the next steps we are developing in UCL. So basically, what I show you is, okay, we can use, instead of approximate mathematical models to represent the biophysical system, we can use advanced simulation. However, then I still use very simple geometries, such as cylinders and just sticks attached to a sphere. If you look at the actual cells, you realize they are much more complex. Like these are two neurons from microscopy, and these are the axons. So really, machine learning gives us a precious tool to literally use as complex as we want systems to really dig into the brain tissue non-invasively with MRI. So the next step, of course, is to improve our numerical simulations and also improve the way we use deep learning to learn from simulation and project into the data. Here you see an example of a preliminary result we obtained from a completely generative model, which means these are cells generated by an algorithm which learned the feature from real microscopy. And we can go down to the highest detail that we want. Now we can use this as a basis of our training of any machine learning algorithm. We are building an arsenal of computational models for any kind of tissue, such as white matter, gray matter, but even tumors. Here is a glioma, and you can see a representative the outcome of our generative model that well represents the configuration of the cells. And just quickly, an example of how from a typical image acquired in clinics, which is completely not, it's just qualitative, it is not quantitative. Using the numerical simulations and machine learning, we can extract quantitative information, such as the volume fraction that can be used to drive proton therapy and to localize the energy of the protons in areas where there are more cells, and use less radiation in areas where there are less. So optimizing the effectiveness of the treatment, minimizing the side effect for the patient. So that's an example of application of this. So I would like to conclude with just a simple take-home message. So in general, in medical imaging, machine learning is used as an iterative process. First of all, you collect some data, and you collect this data with the best prior knowledge you have and with a specific goal in your mind. For example, the MS application I told you. Well, after that, you have to clean and pre-process your data to get the highest performance. Is always a bad idea to just feed the data as they are to your machine learning algorithm. Then you learn the model. Now, what you learn can be different. And in this talk, I show you can learn computational models. You can learn simulation that generalize very well to real data. Then you need to interpret the results, because remember, the machine will learn what they will see. So you really need to take carefully any prediction, but this prediction can be used to consolidate or to discover new knowledge. And then you can start again. This new knowledge will drive you, will guide you to acquire better data in order to train better model and to get further insight into a specific problem. This I would like to conclude. Thank you all very much for your attention. I invite you to contact me by mail or Twitter if you would like to discuss more. also because I am hiring on this. I am hiring for a postdoc on this specific topic. So I would be very happy to discuss further with whoever is interested in the position and in the research. Thanks a lot.
So thank you, Marco, for the presentation. It was extremely interesting for me. I hope also for our participants. So are there questions for Marco? So there is one which I'm not so sure if it is for you or if it was for Francesco. I think it relates also to your work. So we'll anyway, by an anonymous attendee. Do you mind explaining in a bit more details how machine learning can help with denoising? Was it for you or for Francesco? It's a bit hard to say, but you had some.
Yeah. So the denoising, it's really dependent on the technique and depends on the nature of the noise. So in general, autoencoder architecture are thought to be extremely good for denoising tasks. So basically what happens with autoencoders is that your network will decompose the input into a series of high-level features of the input. So the network will learn during the first layers of your model what are the informative features in the input. And these informative features, of course, can be features of the image itself, like the corners, the gradients in the contrast, or can be high level. It can be just something that the network itself learned in the latent space. When you decode this information, you basically retrieve only the useful information. You forget of the randomness. And so the image of the outcome of the autoencoder is, it's by the nature of it, denoised, a little bit denoised compared to the input. It should be exactly the same image as the input, but because the network used a highly representation features to reconstruct it, it lost any randomness that was in the input. Now, this is in general, but in practice, you need to tailor your architecture to your specific task. In MRI, we know that the noise is a thermal noise and has a Rayleigh distribution. So we can build architectures that can be optimized in separating what is signal from what is not informative feature, and then we can denoise them. Just in a nutshell, that's how denoising works when you use deep learning. Then there are other approaches that doesn't use deep learning for denoising.
Okay, thank you. So there is another, so there are other two questions. One, which I believe is very quick, that is, do you need to inoculate water before the MRI? And if yes, how much?
No. We don't. We just use the molecules that are already in the tissue. So water, it's already in the tissue, but you can use carbon. You can use phosphorus. You can use other molecules that are already in the tissue. That's the beauty of MRI. You don't need contrast agents.
And there is another question, which unfortunately is by an anonymous attendee, because he or she clearly is knowledgeable about the topic, who asks how much robust is your method against B-value, Rician noise in the RM diffusion, gradient direction, and what about the problem of non-Gaussian diffusion? Actually, the last one was something I wanted to ask myself. What if you have anomalous diffusion? What happens?
Oh, okay. So really good questions. Yeah, they are in the topic. So basically we can minimize the impact of every single one of these aspects. And that's the design of the simulation and the design of the training strategy is, again, I mean, the challenge with the design of the simulation and the training strategies is exactly this. So for what concerns the direction and the p-value, we use exactly the same configuration that you would use in your MRI scanner to acquire the data. And what we do, we don't use directly the signal. As I show you, from the signal, we derive a series of features. Those features are rotationally invariant features computed mathematically to be reference frame independent. So we don't care, we can minimize the problem of how the brain is oriented in the scanner by not using at all measurements that depends on a specific reference frame. We use only features extracted from the signal that depends on the intrinsic reference frame of the brain of each patient. And as a consequence, your simulation can generalize for any patient in any position in the scanner. For the noise, we add Bayesian noise with a distribution which is measured from the data. So we know with the distributions, which is measured from typical data in MRI, we know what is the distribution of the noise. We can add it on top of the simulation. And anomalous diffusion would arise, anomalous or non-Gaussian diffusion would arise naturally from the simulation because we perform Monte Carlo simulation. So if the system is a complex disordered system with multiple length scale, like it can be polydispersed packed cylinders in plane, they can be a complex system with multiple length scales, then non-Gaussian diffusion can arise in the orthogonal direction. Well, in that case, it's a natural feature that the simulation would automatically bring into the learning procedure. Hope this answered the question.
Thank you. Actually, since it raised another one, I will ask it immediately, and then there is another one by another anonymous attendee, and those will be the last two before the coffee break, since we are a bit late. So you mentioned that it generalizes to any patient. So you use for training other sections of the scan on the same brain? Mm-hmm. Do you understand? Okay. But that
what you do, you train on simulation, where the simulation it's the voxel of one image. So this voxel, then we change the microstructure inside to be to sample all the possible configuration that can happen. So let's say you are interested in exchange time, axonal density, and axonal size. You have 3 parameters. All the possible combination of these 3 parameters generate different voxels with different microstructure. So you can imagine they can represent the healthy tissue, they can represent the diseased tissue, they can represent a mouse as well as a human brain. So they really represent all the possible scenarios given that biophysical model. Now the question is, how accurate is the biophysical model for the mouse, for the human? And that's where the final slides I showed you, we are pushing in that direction. We have a large amount of data out there on single neurons reconstructed from multiple species. Then we have a lot of data from portion of the brain from multiple species. So we can really learn how the structure is and replicate it with generative models, with GANs, for instance, and create, enlarge our training set and explore possible configurations.
This is extremely fascinating, but also a very good topic for the panel discussion. So I will leave it for later. And there is this last question by another anonymous attendee. Hi, Marco. Thanks for the great presentation. Any particular reason to utilize random forests as they are prone to overfitting? How does the performance of deep learning compare to machine learning in your case? I guess she means random forest. So you showed DNN in the slides, but not the performance details. What's the infrastructure you utilize to train and deploy the model? Is it cloud-based?
Yeah, these are really good questions. So the first question, it is true, random forest can overfit, although there are methods that you can use, like gradient boosting, to mitigate overfitting with random forest. Nevertheless, the way random forest explore the latent space is not as accurate as deep learning. So deep learning outperforms always random forest. Now the question is how much, and it does add value to the actual result. My answer is, for the application I have done both. I showed here results with random forest, but I implemented it in deep learning. And deep learning works better. It gives narrower distributions around more accurate values of the prediction, but it's a matter of 5 to 10% improvement that to the actual clinical usage doesn't improve much. However, deep learning can be deployed with a federated approach, which is where the medical field is going on, which answers the second question. So basically, so far what you do, you train your network in-house, and then you send your network to an hospital and the hospital can use it. What can happen is that that specific scanner has different characteristics from the one you assumed when you trained your network. And so your network doesn't perform very well. To overcome this issue, the whole medical field, and specifically us in UCL, we are moving towards federated learning, where the model is shared, pre-trained, and then it's retrained locally, and the weights are sent back to us. Only the weights, not the data. So this will basically make any model more generalizable across institutions and scanner, without the need of moving the data. That when you deal with medical data, medical imaging data, it's a GPDR nightmare. So you can overcome that, and be sure your model will, the more people use it, the more the model will become precise in estimation and can generalize. So.
Okay, thank you very much for your answers, and thank you again for the presentation. So we are already late, 10 minutes late actually, or 20 minutes, 15 minutes late. There is a 10-minute coffee break, but I would like to leave the stage now to the organizers for that. So do we reconvene at 5:10?
Yes, we can take the break. Yes, 5:10 is good. Yes.
Okay, so we talk again to each other.
Yeah, in 5 minutes. Thanks.
Okay, see you in 10 minutes.
Okay, so I hope you had a small coffee or a pause. And now we go on with our last but not least speakers, who is Giuseppe Puglisi from the University of California, Berkeley. So Giuseppe obtained his PhD from CISA in 2017, and he then went on to work in Stanford as a postdoc, and he's now in the same city, but in Berkeley, the other side of the bay, I believe. And so Giuseppe works on the cosmic microwave background, which is the trace, the observable trace of the Big Bang, and is developing machine learning techniques to help remove the foreground of our galaxy so that the cosmic microwave background can be better analyzed. Correct me if I said anything wrong. I believe that was the topic, using a very interesting approach based on adversarial neural networks. So I now leave the stage to him for our last talk. Giuseppe, you have 25 minutes plus 5 minutes roughly of questions. And then we go on with a panel discussion with all three speakers. Please, Giuseppe.
Okay, can you hear me? And let me know if you can see switching the between slides.
Yeah.
Okay. Well, great. Thanks a lot. First of all, I'm really grateful to the organizer because this is so far has been really great to attend. The talk were very, very interesting, and I'm very grateful to be part of this. And so thanks a lot. Yes, and thanks a lot also for the introduction, Luca. So yes, I was asked by, I'm Giuseppe Puglisi, as you know, essentially, yes, and I was asked to talk about the application of adversarial networks for the context of cosmic microwave background. I've been asked also to give a quick introduction also my interest in machine learning, and I would, yes, essentially divide into blocks. The first one would be, if you want, supervised learning with, in general, convolutional neural network, but I'm more attracted by generative networks like VAE or GANs, in particular to the application of 3D modeling could be used for the Milky Way galactic magnetic field, but also for modeling the galactic emission, like we've used this in collaboration with Nicoletta Krakmannikov for the thermal dust emission, but we can use that also for molecular emission, like carbon monoxide, or also this anomalous microwave emission. We can also inject and simulate, and this can be related to what Francesco was saying, so it would be interesting to exchange a bit on these. Also inject the effects of cosmic ray particles into the CMB cameras for space missions. So this is something that I'm really interested in recently. And then the other block is unsupervised learning, like clustering technique, to identify regions of special homogeneity in the galactic emission. So this is, the galactic emission is usually my focus, and I really encourage you when you'll have these slides available to click on this link where there is a useful collection of machine learning papers related to the general topic of cosmology. So since essentially, I would say since the boom of machine learning for applications into science. So yeah, okay. So quick introduction to what is the cosmic microwave background. Usually we call it CMB. Is an acronym. So it's, as has already been said, is the relic of the Big Bang, and it's an emission, the first light emitted by the universe when it was 308,000 years old. So now the universe is 14 billion years old. So you can imagine that this was really the first light, when the universe was a baby. And so, yes, we have this light is, the radiation is perfectly fitted by a black body radiation with a temperature of about 3 Kelvin. but it presents anisotropies to the level of the 100 of microkelvin. So the temperature anisotropies are shown here in this panel. And because of the interaction between photons, electrons, and protons at the time when it was emitted, the scattering is the Thomson scattering. So it yielded also to polarized emission. And so we usually decompose the polarization field into two fields. So the component, the curl-less component, looking similarly to the electric field. So indeed, we call it E modes, as you can see in the second panel, and the B modes, which are the divergence-less component of similar to the magnetic field, which are also an order of magnitude fainter than the E modes, but in general, you see there are 3 orders of magnitude up to, or 2 orders of magnitude fainter than the temperature anisotropy. So usually we can expect order of a few percentage polarization fraction for this radiation. And this makes essentially makes a really interesting goal or to detect in particular polarization for the CMB, because if temperature and E modes are sourced by density perturbation of the when the universe was at the time of inflation, so those are essentially macroscopic, quantum fluctuation that became a macroscopic with the inflation, this exponential expansion. The perturbation of the space-time metric at the time of the inflation are essentially sourced by, are directly smoking gun of the B modes. And so you can imagine these kind of gravitational waves, stochastic gravitational waves propagating at the time of inflation. So if you want the application, it's less, how can I say, useful for respect to the previous speaker. I feel a bit ashamed by that because you see application related to earthquakes or tumors, cancers, which is really great to see that. This is more aiming at addressing the questions from the very beginning, of our intrinsic curiosity. So indeed, we are probing the universe at the very super high energy state. So we are talking about 10 to the 16 giga electron volts. So B modes are very attractive, but they are not detected yet. So we have set upper limits, and so the most recent were from BICEP2 Keck collaborations from a ground-based experiment in the South Pole. So why is this is tough? The most problem, the toughest problem is that there are actually, being the CMB, the first light, there are all the lights emitted from stars, galaxies, our own galaxy that acts as a sort of foreground. So everything in front of this background. And our own Milky Way, the galaxy, is really one of the toughest. So you see here in terms of frequency, frequency bands, you see the emission from the synchrotron, so electrons spiraling around the magnetic field lines. And so you see here the amplitude map of these emissions. So you see this synchrotron is described very well by a power law. And then there is the thermal dust, as I was saying, that is emitting polarization because of the dust grains aligned. Imagine like ellipsoids aligned along the magnetic field lines. And this yields to a polarized emission too, like the synchrotron. And so you can see here the level of the CMB and a polarized anisotropies compared with the foregrounds. So and you see that they are totally subdominant. So this is the first challenge. Even in the region, in the clearest regions where you see less emission from the galaxy, so far from the galactic plane, which is shown here as a stripe, right, vertical, sorry, or horizontal. There is this contamination that is actually can mimic the B mode from primordial cosmic microwave background. And the other foregrounds that we actually, I already mentioned, they happen to the smaller angular scales. So, and they are kind of related as usually also at low frequency. So let's say below 100 gigahertz, those are synchrotron emission, but emitted from the far distant galaxies, extragalactic sources. And so you see here an image of the SPAS survey where you see sort of point-like sources, but those are actually AGN, active galactic nuclei, emitting synchrotron at very, very distant from afar. And being synchrotron sources, this is also polarized, and then you can kind of see these point-like sources. These are essentially will contaminate our CMB polarization. On the other side, we have at higher frequencies, there is still the same mechanism, but this is emitted from far, from the galaxies. And so there is the thermal dust from the galaxies, in particular the star-forming galaxies that are full of dust that can actually emit and disturb, contaminate the foreground emission. So at above you see those are kind of sources that we see, but those are kind of at smaller scales. So, well, the take-home message, if you want, is that high-resolution polarized galactic foreground maps in the microwave are very, very hard to get, and those are those are critical to estimate, to have a under control estimate of our of the CMB signal, polarization signal, the B modes. And why small scales are highly contaminated? You can imagine those scales are mostly affected by instrumental noise, fluctuation pixel per pixel, and also extragalactic sources. So far, what was how to address it, or kind of tackle this problem, is to either mask all the sources and the galaxy. As you can see, for instance, this is a mask of the galactic plane in equatorial coordinates, and so here for the Simons Observatory collaboration, a future experiment. And all these point-like masks, holes, those are essentially the radio sources expected to be observed by Simons Observatory. And so you see that's really, really aggressive, as you can see. And otherwise, instead of masking, you can just degrade your maps to a lower resolution, let's say from the Archimedean to 2 degree, so that you increase the signal and decrease the noise. So you increase in general the signal to noise ratio for those maps. But then you pay a price. Either you get rid of pixels, so you reduce the observed sky, or you pay the price of giving away the high resolution maps that you have observed. So the question that I had 2 years ago was, can machine learning help on this? And you can see that these are, in the last year was interesting to see that we actually published 2 papers that are actually addressing this problem. The first one was in painting galactic foreground intensity and polarization maps using convolutional neural networks. So used essentially, yes, addressing the aggressive masking, or instead generate smaller angular scales, and this was a work with Nicoletta Krakmannikov, addressing smaller angular scales with low resolution maps. And so using essentially a GAN-based algorithm. I would like firstly to address this, the most recent paper, and then if I have time, I will go with the in-painting one. Okay, so how does about the sub-degree angular scales of dust maps? You can see that essentially we have we can estimate the angular power spectrum of the dust emission, and the angular power spectrum is essentially the square, the modulus of the Fourier transform of the map of the dust. And as you can see, the spectrum, both in E modes in the top panel and in the B modes in the bottom panel, the spectrum looks like a scale invariant, a power law, no? A scale invariant in the power spectrum, it means that there is no typical characteristic scale. So there are no peaks as you can see, for instance, this is the power spectrum of the E modes of the CMB. So there are angular scales typical related to the horizon, the sound horizon at the time of the CMB, when the CMB was emitted. But the DARST is scale invariant. So this means that essentially you can imagine the emission of our own galaxy like a fractal-like structure. Moreover, the Planck satellite observed dust temperature maps, not polarization, up to the degree at the 12 arc-minute angular scales. Whereas for the polarization, we had fewer smaller scales available because of essentially the signal to noise ratio. It was worse. You can imagine this because the polarization is always 20% lower than the intensity, the temperature. Yes, and so usually the current galactic models have small scales, so below the degree scale, included with the Gaussian realization, so of power law power spectra. So you extend this power spectrum to lower to smaller scales, so higher multiples, the inverse of the angular scale, and you can do this just injecting Gaussian noise, kind of consistent with the power law. But you know very well, and you can imagine why, that the galactic emission is highly non-Gaussian. Imagine for instance, a nebula, super strong, and then with a background, you definitely can imagine this as a not Gaussian field. So for instance, the average is not 0. And imagine the standard deviation. So it's not Gaussian, but so this is a really bad approximation, I would say, although it was the easiest intuitive approach that was made in the past. Okay, and so the question was, can we use a GAN, a neural network, in particular an adversarial network, to learn the scale invariance of the foreground that is observed here in the power spectra, and inject sub-degree non-Gaussian scales? So we want smaller scales, non-Gaussian. And the answer was forse, which in Italian means maybe. But this here is an acronym for foreground scale extender. And so the idea, as you can imagine, is that you have, where you have available data sets, you can train a neural network to learn how to convert from the coarse resolution maps, like the 1 degree, to the 12 arc-minute map. And then you can extend these to higher resolutions where you don't have essentially high resolution maps. So you, for instance, farther where the signal to noise ratio is lower, or there are no data available. So we, as I mentioned already, we made use of generative adversarial networks, the GAN, and so I suggest you to go to the Ian Goodfellow et al. 2015 publication, which was the first proposing this approach, this network. And quick introduction on that, just to give you an insight, but it's really an insight, not much than that. So how does it work? It's a minimax adversarial game. So there are two networks, the generator network that essentially try to learn this, how to pass from a low resolution map to a high resolution map. And then there is a discriminator, which is able to, which is aimed at discriminating or distinguishing the mock, so the generated smaller angular scale maps with the real ones. And so, so the generator tries to minimize the loss function, whereas the discriminator tries to maximize it. So that's why it's called the minimax adversarial network. So, and we can say that this is this network converges when essentially the generator is so well trained that is able to fool the discriminator. Yes, and so this is, for instance, an interesting thing. You can, this was firstly applied for faces, human faces, and it's impressive. If you go to this website, thispersondoesnotexist.com, you see these are totally plausible faces from humankind, I would say. And actually it's interesting because although this is a discussion whereas the gun can be biased towards some race or some gender, actually it's starting to produce similarly faces for white people or African American or actually or Asian, and so it's really cool. For our case, we applied a DC gun, so a deep convolutional gun. The reason was that we have tried several architecture, but we wanted we started with an architecture that was already similar, applied in similar context. And it's a deterministic network, so it means that given a large scales coarse resolution scale map, you generate just one realization of that. So here we applied for 20 by 20 square degree maps, images. And so, yes, you have the maps are at 80 arc minutes resolution, and the outputs will be maps at 12 arc minutes resolution. Yes, and this is, for instance, the first application. So you see a test on the temperature maps, where you have the coarse large-scale maps, the real observed maps, and then the generated ones in the rightmost panel. And you want to also assess the statistical properties in terms of the power law or this angular power spectrum are consistent with the one observed. And so here you see for the three images, we estimated the power spectrum, and there it's, as you can see here, is perfectly consistent with the power law, as I already mentioned before. It's interesting also that, of course, this network never seen is essentially from the test set, so it doesn't know what is the real ground truth, and it's impressive that we are able to reconstruct similar structures given the coarse map. Here, for instance, essentially the gray dashed line is the power spectrum of the large angular scales map, and it's dropping at L, so the multiple less than 400, so it's actually 200, between less than 300, and so this drop is due to the fact that we don't have power at smaller scales because of the resolution. Okay, but in polarization, this is really tough. Because we don't have high resolution maps, as I already said. So because of this, we assumed, we did a strong assumption. Because of lack of data, we assumed that the polarized dust emission, parameterized by the Stokes parameters Q and U, essentially at smaller angular scales follow the same properties, statistical properties of the unpolarized, so the temperature emission. And so essentially the training was to perform, to find the best results when we are able to reproduce those non-Gaussian features from the temperature at 12 arc minutes. So the inputs are essentially Q and U maps at 80 arc minutes. And yes, and you can see here a comparison of these two approaches. In particular, usually there are the large scales and for Q and U, and then the polarized amplitude, which is the square root of Q square plus U square, and the comparison of the mock generated maps and the maps with smaller scales from the Gaussian approach. And so, as you can see here, they are kind of similar, but of course you see that is more highly non-Gaussian, at least you can see it perceptually by eye. The statistical properties are consistent, but of course you see that higher order statistics estimated with the Minkowski functionals are actually different. So I don't know how much time I have, but so the Minkowski functionals are a way to estimate they describe the morphology of structures in an image. And so in a d-dimensional space, there are d+1 Minkowski functionals. And for an image, we have 3 Minkowski functionals that describe the area, the perimeters, and also the connectivity of an image. So how to estimate that? If you have an image like this that goes from 0 to 255, a bitmap image, you set you run with a threshold. Essentially you use a threshold, a row, to set all the pixels that are above and below this threshold. And so you see, as a function of the threshold that is increasing, how the pattern, for instance, the area of the gray, of the white and black regions changes, the length, and also the connectivity between the islands. You see the black islands changes. So you can, for this image, for these 2 images, actually, you can see the Minkowski functionals as a function of threshold, how they change. And so we applied this estimator to assess the higher order statistics, in particular for our case. And the Minkowski functionals here are shown for the 3 cases. So for T, for temperature maps, you see that the real Minkowski functionals are perfectly consistent with the generated one. And so for the 3 Minkowski functionals. But it's interesting to see that what is the error in the higher order statistics when we use non-Gaussian scales with the Gaussian scales compared with the Gaussian scales in the case of polarization maps. And you see here how the departure of in orange is the generated polarization structures with respect to these to the green one that are essentially the Gaussian scales. And so you can, given the fact that you can estimate quickly for a Gaussian random field analytically, you can estimate the Minkowski functionals. I can tell you that the Gaussian green Minkowskis are perfectly consistent with a Gaussian field. And so whereas the departure means that we are injecting non-Gaussian scales, especially shown here as the orange boxes, orange shaded areas. Okay, the other case.
We have 1 minute.
Okay, yes. Okay, I'll jump to the, if I have time during the panel, I will talk about that, if you're curious. So summary, the generative adversarial network have been proven to be really useful to generate signals. And this is the first time that you applied GANs on polarized foreground emission. So then we have estimated full sky maps, as you can see here in these images. So we actually you can estimate what are the differences between the large scales and the generated scales are shown here as residuals. And of course you can imagine, and as you can see, the residuals are happening at smaller angular scales, so like pixel scales. And several improvements are expected. So we are expecting using other simulations and different architectures. And with this, I thank you for the attention, and yeah, I'm happy to take any question. Thanks.
So thank you very much, Giuseppe, for this very interesting talk. So we jumped from applied physics to the most fundamental questions, right? So
yeah,
I think that is very interesting as well. So we shouldn't only focus on application, otherwise both are very, very nice. Okay, we have time for questions, about 5 minutes, and then we go to the panel discussion. So again, if anyone has questions, please write them in the Q&A. Otherwise, I will ask some question myself. Well, while they think about some possible questions, I have one myself. So you train the GANs starting from some pages of data where you have enough resolution, if I understood correctly.
Yes, yes.
And those are the one when you have a high enough signal to noise ratio. How good is the assumption that they can also be representative of the portions where you do not have a high signal to noise ratio?
Yes, so it's a good question. Yeah. So what we did indeed was to train where there is a signal to noise ratio larger than 8. So these are the patches in purple shown here. And we actually excluded the galactic plane because it's actually saturating the emission over there. So the interesting thing is that you have at a larger angular scales, at the degree scale, you have the signal to noise ratio. It's also good for temperature as well as for polarization. So this made us confident in exploiting these patches. Also I mean, where we have essentially at higher galactic latitudes, where we have patches available only at larger angular scales, so coarse resolution. Yeah, it's tough, although it was a certainly a kind of a coarse approach, but we wanted to first demonstrate that this is actually doable. Then, of course, there are several other attempts that we want to apply. For instance, this is the assumptions that we have made, not only for instance for polarization, are really can be actually strong, and but of course if we don't have data to probe this assumption, this is the this is the list that you can do. I don't know if it makes sense to you.
No, it does, of course.
It's a trade-off between the available data that we have and try to exploit the state-of-the-art techniques from neural networks.
And you cannot repeat the experiment. I mean, there is only one realization of the
right. Yes. That's also the other point.
Okay, there is a question from Sophie Bini. Can we give the mic to her? Maybe.
Hi, sorry. And I just want you to ask in the first slide, I see something about unsupervised learning and clustering techniques. Can you say something about it, please?
Yes, thanks a lot. I have a slide on this. It's so you imagine that you have essentially with the same maps that we have shown you before, like these, right? So you want to essentially identify patches where the emission is more homogeneous, right? So when we say we want to use clustering techniques, where so essentially where we can divide the full celestial sphere into smaller domains, but by being informed of the galactic properties per se. I don't know if this makes sense. So usually what you have, so it's a map of the of a parameter that describe the emission, like power law. You have a spectral index for the dust, and then you have also uncertainties accompanying those pixel per pixel measurements. So you can imagine, for instance, beta is the power law index, spectral index, and so and you can well, I mean, just intuitively imagine that beta is a sort of a Gaussian, a normal distribution with average value, mean value, the measurement of beta per se, and then the width is given by the uncertainties. So here you see few pixels shown here. So you have, for instance, betas where the values of beta where there are larger uncertainties, like the red, the orange, and the yellow, or also values where the beta is really highly measured, I mean, with high signal to noise ratio. So like this distribution here in cyan, in blue, and purple. So those are in the 2D, if you want to imagine, in the 2D plane of beta sigma parameters. So beta, the mean value, and sigma, the uncertainties. They look like these. They look like these kind of islands, right? So we want to perform clustering methods, and in particular, I'm using spectral clustering. So to essentially address, identify these patches, given the information that we have from the uncertainties and the measured values, but also the fact that those pixels lies in a manifold, in a two-sphere, right? In a celestial manifold. So, for instance, the Euclidean distance is not really applicable. So what we did was to use the Laplacian to use the Laplacian defined in the two-sphere, so that we are able to identify the distance, estimate the distance between a pixel and the other, so the so-called affinity, considering the geometry, so the differential geometry of those pixels, so defining the manifold, plus this extra distance defined by the fact that of course, where you have larger uncertainties, is easier to clusterize the pixels, or where you have instead where you have a high signal to noise ratio, it's very hard to clusterize them. And I can show you. I don't know. First of all, if it makes sense to you, maybe it's there are too many concepts.
No, it's okay.
Okay. Okay, so, and you can imagine, so these are the results. So here we minimized, so we have defined the optimal cluster distribution. So as I said, clusters are patches by minimizing the between and within cluster variance. So there are two parameters that define that. So you see these surfaces where you see yellow, these are the minimum for different parameters describing the emission of the foregrounds. And you can see, for instance, here how the cluster size changes as a function of the galactic latitude. So we are not considering the galactic plane, but you see, for instance, closer to the galactic plane, so closer to the blue mask, you see smaller clusters, smaller patches, where when you go far, you see these patches are really larger. But so this is essentially, we are also showing that clustering can be useful also to identify those patches, because you see that the morphology is kind of driven by the galactic emission. Of course, you are not familiar with that, but there are a patch like this kind of plume is a morphology that is observed in the galaxy. I don't know if you can. Yeah, you can kind of tell it here. So it's a really an ongoing project, but it's really is really becoming very promising.
Okay, thank you.
Okay, thank you again, Giuseppe. Since we are late for the panel discussion, I would like to invite also the other speakers to connect, and I think we could start the panel discussion immediately. I would also like to ask the organizers if we can go a bit over time, because otherwise the panel discussion is going to last 11 minutes. Right.
Yeah, I can speak, and I mean the channel will be open for a while, so at least till 6:30. So you can definitely go a little bit longer.
Okay. So we keep. In that case, let me start the panel discussion with the 2 unanswered questions that we have. And then I would like to propose some more general questions to all our speakers. And also I invite again all the attendees, everyone from the public, to also propose more general questions to our speakers. I will relate them, or I will invite you to talk. So the first question, the 2 remaining questions are both for Francesco. The first one is from Claudia Borredon, who had to leave before, and I will relate it nonetheless. Perhaps she will look at the registration, at the recording. So the question is the following: is there a specific motivation for which you choose the ReLU and not, for example, Riki, ReLU, or other activation functions?
Okay, that's a good question. And actually, there are 2 answers for this question. The first one is that when we started the study, the ReLU function was very famous in deep learning process. And you know, these activation functions, these methods to optimize towards your minimum, towards your global minimum, are something that always are updating, always are improving. And let's say we started with the ReLU, and we set our problem with this ReLU applied to our neurons. So we characterized our network, we trained our network with this function. Then we also trying to make a comparison with other activation functions. Why not? We tried parameterized ReLU, which is something similar to a leaky ReLU. And we also tried an exponential ReLU, which are 2 activation functions which that solve a problem of the ReLU, a theoretical problem of the ReLU. This problem is that when you get a negative value for the ReLU, the gradient in that node somehow dies. And it's very unlikely that you can resurrect this node again. And so there are different functions that try to solve this, and the leaky ReLU is one of them. But actually, during the optimization of our model, we didn't find any difference using ReLU or, for example, a parameterized ReLU. And actually, we got worse results because, it depends on the hyperparameter we were using and also on the problem itself. Which kind of activation function is the best. So the question is that first we use the answer is that first we use the ReLU because we knew about the ReLU. It was a good choice for our problem. And then we tried also to upgrade towards best solution, but we didn't find any difference.
Okay, thank you. Also, I would like to invite you to keep the answers a bit more concise on the technical questions, because otherwise, we only have 40 minutes. It's very interesting, but we have to try to explore a bit more. The second one is a tricky question about the loss function. So that you showed a U-shaped, a convex function. So do you use that? Is there no risk to end up on in a local minimum?
I totally understand the question. I actually was expecting it, because I show you just a sketch of how the minimization problem works, showing in the simplest loss function you can have, which is a parabolic function, with one global minimum. But unfortunately, the problem is not, the function you have to minimize has a lot of local minima and global, and one only the global minimum. And this is an open problem, I think, in the optimization of the convergence of these neural networks. And there are many ways in which you can jump over this local minimum. For example, you can use adaptive learning algorithms as optimizers, like for example, ADAM or ADAGRAD. Or you can use the momentum, the parameter of the momentum in the optimizer, which is somehow the inertia of the gradient. If you fall in the local minima, you still, at the next step, keep the same direction with the gradient thanks to this inertia, and maybe you can jump over it. Or you can design a learning rate scheduler in which you decrease learning rate, then you increase it a bit, then you decrease it another time in order to avoid to fall in local minima, which represents worse solutions.
Okay, thank you very much. And now we can start with the more general questions. So there is one who is for all three of you, for one of the attendees, Shabazz Alvi. I'm sorry if I mispronounced your name. And I will invite the attendee to pose the question themselves.
Hi, thank you for the very interesting talks. Just to start it off, I'm studying cosmology. So the question, although is general, but my personal interest is within the context of cosmology. So the idea is, so the question is basically this: that when you have a training data for your algorithm to learn the weights and all this stuff, right? The training data is not going to be pure in the sense that it's not going to be free of the systematic effects of the way that the data was obtained, right? So my question is that how can you be sure, or is there a way to understand how much that systematic affects the learning process? I'm very inexperienced in this particular field, in this particular applications. So I'm just concerned that, as I understand, mostly that the algorithm is treated as like a black box most of the time, and you don't really know what it's learning. You just basically understand it as a more numerical recipe of making predictions. So the question is that within the context of the question, how can you be sure, or how do you make sure that the systematics imprinted in the training data is not affecting the output or the predictions of the network? Yeah, thanks.
So Giuseppe, I believe you should start.
Yeah, it's a good question. Thank you, Shabazz. No, it's, yeah, I don't really know. It's honestly, I've been thinking about that. Recently I found a really interesting new technique that is called the self-supervised learning. And this is really, I think the answer will be to really dig. And there is a paper I can suggest you. I rewrite it in the chat from George Stein. Really came out, I think, last December, where they actually address that. And so the answer to the question, I would say, really to know what's going on in the latent space. You know, the representation from, let's say, an image to the low dimensional vector. This is the latent space when we apply, for instance, an encoder network from, from an image to a low dimensional space. And so there is really, I would say, if you really have control of that, and you have an understanding of that, you can really, I would say you can really inject, for instance, systematic effects and see the effect at the end on your predictions. But it's really something I would say is new. One, because the application of machine learning to science are really new, I would say. I mean, it's really recent. And so perhaps a scientific approach onto these, I would say it's it was less, addressed. I mean, if you read, for instance, the GAN papers, or they don't really care about, phasing reconstruction or phases reproduction. I will say that they didn't. This process was not addressed very well. But when machine learning now is being adopted into science, I think there is more also curiosity on that. So I think I would say this is why the answer is really tough to address, from my opinion.
I add something? So I think it's a really good question, and I totally agree with Giuseppe, but this question is, as you said, is general, and it's particularly a crucial question for medical imaging, because if we predict, for instance, we get a low res and we apply super resolution, and we predict in a patient where there is a lesion, we predict something high resolution, we need to be sure we don't introduce spurious lesions or we don't miss an existing lesion. So we are working on this, and we came up already, my colleagues came up already with a few solutions to that. One employs Bayesian deep learning, where basically the generator that we saw Giuseppe using, it's in the cost function. Also, the volatility of the prediction is a parameter that is estimated. So when Giuseppe goes from the low res to the high res, the generator doesn't output only the mean prediction, it also outputs an uncertainty on the prediction for each patch. Now, this uncertainty has two terms. Depends on the task. Let's say the Giuseppe task. In his task, there is an intrinsic uncertainty, which is going from one to many solution. So one contrast at 1 degree can map into multiple 12-degree resolution that gives you the same contrast. And there's no way you can avoid this with more data unless you can acquire at that resolution. So this uncertainty can be quantified with an heteroscedastic model inside your generator. And we have a work on this, and I really think it would work really well with Giuseppe application. I can share after. So we have a way for medical imaging, but generalized to any kind of patch-wise super resolution approaches, where you get out an estimation of this intrinsic uncertainty, as well as an estimation of the actual prediction uncertainty. And that is the one corrupted by data quality. So if you have more noise, you have a higher, if you have lower SNR, you have a higher error in your parameter, in your prediction. The second one, you can compute it using the generator that Giuseppe has, using dropout after each convolutional layer. And you collect the latent space representation at each dropout, and you can compute the mean and the variance of it. And basically you can compute what is the mean and variance of your final prediction. So basically, in medical imaging, this is a serious issue, and although it's still early stages, there are already a few solutions. One is this one I just told you, and I think it can work really well with Giuseppe data. As I saw, the second prediction showed quite of a mismatch, and these maps can really tell you where and why you predicted low. Is it because his data are not good enough, or is it because this one-to-many problem is too difficult to untangle in that region?
If I can add a little piece to the wonderful answer the other speakers gave to you, is that dealing with systematics and with error is one of the skill for every high energy physicist, particle physicist, because we spend a lot of time actually evaluating this error on the input variables we measure, on the variable, on the observables we measure. We actually in this field of application, there is a very spread technique, which is, for example, we usually train our model on Monte Carlo, and then we apply the models to real data taking. And since our Monte Carlo is usually really precise, but still different from real data and different in each variables, and this difference then sum up and it can cause a mess in your prediction on real data. We try to evaluate the impact of each systematics on the output of our deep learning algorithm. So we start varying the input variables with 1 sigma, 2 sigma error, 3 sigma error, and we see how much this systematic impacts the prediction of our X deep learning model. This is one way we do that. And the other way to deal with the difference between the training set and the real data taking was, for example, the case I was quoting in my presentation, to use a domain adversarial neural network or some domain adaptation technique to make your algorithm less sensitive to the difference between the training data set and then the real data on which you want to apply.
Okay, thank you. Thank you all.
Thank you so much for the papers as well. Thank you, and thanks.
And thanks for the question. So there is another questions by Giorgio Cartechini, but before that, I would like to ask one which kind of introduces perhaps also what he is asking. So I remember when I was doing my PhD, my advisor was not so keen on anything that was neural networks related, because and that was quite a shared opinion in biophysics back then, because it was very, very difficult to get some insight. So you get your model works a bit as a black box, back then at least. You can do some predictions, but his opinion was, okay, but then what understanding did you get out of this? What do you think is right now the role of machine learning in science, considering that while industry can be very, very happy with just giving some answers without really understanding why that works, we would like to instead understand why it is like that. So what were the steps that were taken in the meanwhile? And do you think is a problem that has been solved? Is still something some work still to be done? And since we started from Giuseppe last time, perhaps we can start either from Marco or from Francesco.
I can start answering if you want. I recently had the occasion to read a paper which was which titled "Explainable Machine Learning for Scientific Insights and Discoveries." It is actually a really interesting paper because it makes a list of important publications with deep learning methods, machine learning methods, and it tries to tag which publication explains the method, explains the algorithm, and then tries to interpret what the networks learn and tries to give an explanation why it learns better than some analytic methods or whatsoever. So if you want, again, it's very funny also. It's a bit critic on that, but it's really funny. But for what concerns me, or what concerns my field of research, these algorithms are used as a tool to reconstruct some objects, and that then are used in higher level analysis. I mean, there is always some theory on which you compare the distribution you measure, and this you do it by yourself. You don't use a neural network to do this piece of logical path. I mean, at least in our field of research, we use them as a powerful tool, as all of the other speakers told us also, but not to. I mean, we do not let them to substitute at the end the higher level analysis that a physicist must do to interpret and compare with models.
Yeah, I can add to that also in my field there is an open issue which is of central importance. There is a lot of discussion about interpretable deep learning, interpretable machine learning, and I think there are contexts like the one I've shown you where machine learning is used as a tool, like Francesco said, for which everything is absolutely uninterpretable. I know exactly what my network does. I know exactly how it represents the input, and it makes sense the way it represents. Something that I think it's a little bit misunderstood in general is that machine learning is not just a random collection of tools. They are designed with a purpose, and there is a rationale behind. If you use a generator, the generator has that architecture because it is known exactly what each layer does, and it's known that it's optimal to reach your solution. So the interpretability of how you build the architecture, what this black box does, happens when you use deeper and deeper architecture, when you start losing the when the mathematics layer after layer becomes too complex, basically, and you lose track of what's going on. That happens, but it's not the majority of the cases. The majority of the cases, the networks can be written mathematically very precisely, and you know exactly what's going on from input to output. One more question I would like, no question, but one more point is how much we can learn from this black box. So are these deep learning actually useful to learn? So you don't use them just like tools. You use you know, fitting tools or whatever, regression tools, classification tools, clustering tools. You use them as exploratory tools. Can you? Well, there is a field, neuroscience, where this is very much the case. So deep networks in the reinforcement learning framework are used to understand how our brain learns, how we learn to memorize picture, how we learn to walk, how we learn the equilibrium, how our eyes transmits the intensity of the light to our brain and its process. There are a lot of works where basically the only way you have to understand how this neuron to neuron interaction works is to build a deep neural network, which is architecture-wise identical to the organization of the neurons in your brain, and see what's gonna happen when you put that network in a reinforcement learning framework. And that's, to me, is very exciting. And we shouldn't forget that neural networks were born in this way. I mean, they were born trying to understand the neurons, and then they discovered, oh, actually they are excellent pattern recognition machines. They are excellent approximator of any nonlinear function. So we can use them for regression, classification, generation of reasonable phases, and so on.
Quick comment, just because I think those the answers were very, very explanatory, I would say. yes, I would use those, I mean, criticism when we approach machine learning. I totally agree. I mean, approaching that as a black box is, I would say, is not very scientific. And this also involves some creativity, which is not lacking in the context of science, I would say. Creativity, I mean, like, for instance, changing the quantities, the metrics that evaluate for instance, the quality of the reconstructions or the predictions. I was kind of an example can be, for instance, changing from the you know, the peak of signal to noise ratio for the quality of the reconstructed images within painting I was doing with estimating the Minkowski functionals, which is kind of something, a metric that is more intuitive, I would say, and also does the job that I wanted to do. I mean, for instance, not only answer to the distribution of the pixels, but also answer what are the higher order statistics, right? So I would say that, yeah, it's the criticism is totally needed, but in the meanwhile, yes, it's totally, as Marco was saying, it's I think there is something there that is worth exploring.
Thank you very much. So let's move to the questions, to the question asked by Giorgio Cartechini, and I invite him to ask himself. Perhaps he is not connected anymore.
Can you hear?
Yes.
Yes. Okay, thanks. Yeah, okay, it's quite general question. I think, as I said, one of the most interesting, at least to me, usage of deep learning and machine learning is to discover new models and new physics. It has been briefly mentioned, I believe, also in previous questions. And I'm not expert on this, so can you comment on this topic, say something, I don't know, major issues, the approach used, or something?
So Marco, can you start?
Yeah, I can start. I think this is very much field dependent, and so I can answer to perhaps applications I'm more familiar with. And I mentioned some just in the discussion before. I think every time you use machine learning algorithm, it gives you useful information on the physics behind. So again, when, for instance, it takes the input and start learning a higher representation of it, those higher representation can be informative, can tell you, okay, you want to know what is in your input measurement, the most relevant feature, according to me, that enables you to measure more accurately the diffusion coefficient of this diffusing molecule, where we know that, now I project it to my field, we know that the density of the membranes, the permeability of the membranes, the arrangement of the membranes can be all factors that determines the diffusion coefficient. But the network can suggest which one of these, for instance, is totally negligible in this, according to my input, because there's not enough information there. At the same time, it can inform me how to improve my measurements. So there are a lot of applications where you train a machine to tells you how to measure the input in such a way to get the best sensitivity to the output. Again, I want to have the highest sensitivity to the diffusion coefficient. There are too many parameters on the MRI scanner I can change. Like there are 10, for instance. Already how many combination of 10 parameters that can assume any value you are able to explore with your mind. Very few. The deep learning can, it's an excellent pattern recognition devices. So it can really explore the manifold and tells you in reasonable times, listen, that's the best combination of these 10 parameters to measure that diffusion coefficient. So for instance, measurements optimization, that's knowledge discovery, because you do need power, computational power to do that. Deep learning is a very efficient way of dealing with this question. And there are many others like image reconstruction. So machine learning can substitute compressed sensing in all the aspects and outperforms it by many times. And this means that it tells also, you can also learn what's the relevant information to collect, and you can focus only on that. And again, compressed sensing is based on a very close form mathematics, and it's not able to give you the same answer that instead the deep learning approach. So again, it's a bunch of examples, depends on the specific application. In your case, I'm not familiar with your specific application, but hopefully this example, you may translate this example for your specific case.
So perhaps I would like to clarify, to ask George to clarify a bit the question. In order to do that, I will also introduce an example that I happen to know that was quite interesting to see, which is the Feynman AI 2.0, which is basically a symbolic regressor based on neural networks. So that literally builds symbolic models out of a set of data, taking into account the symmetry of the system, dimensional analysis, other kind of things. So perhaps this is what our attendee had in mind. But I would like to ask him to clarify in which sense discover new physical models, because in the end, when you have a machine learning approach, you induce from your data something more general. You try to find some pattern, while the model, at least to me, involves some more creativity. So you get all this, you get the patterns, etc. Then you try to start from a vision of the world and introduce a model. Could be, I mean, now we have the standard model for particle physics that took years, and that took also a precise change in the of how we saw the world before it could be put forward. So what do you mean by model?
Okay, can you hear? Okay, no, I mean, it's really general. I've read, and not read some paper, just read that, for instance, deep learning and machine learning is used to actually discover differential equation governing, so the governing law behind some models, or also they're perhaps trying to going beyond the standard model, so to discover, to test and to stress the models to understand the physics behind. For instance, in previous question, it was mentioned how somebody's trying to understand how the brain works, and this can be, for instance, to using machine learning and deep learning to try to discover something that we do not fully understand. I mean, I understand that somehow it's the standard way, but I think it's also push forward. I mean, deep learning is push forward to actually understand something that we do not actually know at the moment. That was the question I had. So how do you proceed? I mean, the idea, I think, this is what I think. If the idea is okay, the universal approximation theory tells us that ideally you can approximate any function with an arbitrarily deep neural networks, and okay, that's a good starting point. But how do you actually use a neural network or deep learning models or whatever to understand the equation behind behind the physics? That was my, I don't know if it's a bit more clear now, my question. It is, I mean, really general.
Just reacting. It's my knowledge is really scarce on that. I was very interested by what happened with AlphaGo. This game was by DeepMind, I think was the people organizing that. So it was, you know, Go is a game very hard to find a machine able to beat the player. It's I think a Chinese game. But recently, AlphaGo team, so in DeepMind, were able to beat that, the world champion. And how essentially the AlphaGo was playing totally a different game, so totally different strategy respect to so essentially it was able to fool the player because it was playing a totally different strategy. So yes, I mean, I think it will be interesting, but my understanding is that it's still something really unexplored. I would say, I don't know.
If I can quote the only example I knew about machine learning or deep learning application to discover beyond the standard model physics. When I was at CERN, I listened to a talk of a guy that was trying to apply a trained algorithm which was trained to discover anomalies in distributions which we measure, like for example, the mass of a particle in a collision we generate. Now you try to observe this distribution and to perform a statistical analysis in order to find deviation from the standard model. And this neural network was trained on different beyond the standard model samples generated with Monte Carlo. And then it was used to compare this knowledge it has on the beyond the standard model distributions. It compared this knowledge with the actual distribution we measure with our detector in order to see for compliance between the distribution and other beyond the standard model spectra, a better compliance comparing to what we have just with the standard model. So it tries to introduce extra term in the equation and see if the effect of these other terms is more or less more compliant with what we observe with respect to the standard model. This is the only application I know about this in high energy physics. But if I can add, it will be not enough. I mean, you really have to find, if you want to publish this result to the scientific community, you really have to find an analytic model which explains what are and which are the terms you add to the standard model Lagrangian that reproduce better the spectra you observe. You really have to have an underlying theory that somehow is also can be extracted maybe from this model, because you know the correlations in this model. You can try to explain why the new term is more representative of the standard model Lagrangian. But at the end, you will need a real analytic model if you want to claim it as a discovery.
Okay, thank you very much. It's almost 6:30, so I believe we have time for, although this was a very interesting topic, but I think we have time for two questions more, maybe three. So one is written in the chat, actually by one of our organizers, and I will ask him or her, because I see only the International Physics Network.
Okay, so okay, thank you all the speakers for the great talks. My question is about adversarial attack. So we already seen in some fields as autonomous driving that you can fake all the algorithms by putting some sticks on the signs you find on the streets. And okay, that is okay. Maybe there's some people still talking. Let me just disable the. I'm sorry, just one moment. Okay, sorry. So I was wondering if there is some efforts in science, let's say in physics maybe, to cope with these issues. For example, talking about the MRI, maybe some adversarial attack on the infrastructure where the hospital is running could lead to fake diagnosis. Or, for example, for the high energy physics field, that could lead to the discovery of a fake particle. Let's say maybe you can fake the energy released in the calorimeter, and then you say, oh, I found the supersymmetric Higgs boson, let's say, for example. So if you have any comment on...
Before that, let me rephrase a bit the one for the high energy physics and astrophysics community. So suppose, for example, a cable in your detector under the Gran Sasso is slightly detached, or there are some errors in the model used to clean the data from a satellite. That would be an adversarial attack, although not intended, I guess.
So I can start maybe from my field. There are many ways you can try to mitigate this, and so one nice example of exactly what you pictured is there was this publication using a CNN to classify who had cancer and who had not. And for some reason, the CNN got high performance on classifying on this classification task. And the surprisingly was that it got higher performance than the best experts neuroradiologists. So that was kind of suspicious. And after digging more into the methods and the work, it came out that it was learning one of the label. So you have typically you have an MRI image, and then you have the date, you have the name of the patient, you have the resolution, and then you have a label like head first or feet first. The way the technician was putting inside the scanner the patient. And for some reason, that hospital, they were putting always head first the healthy subject and always feet first the deceased. And so the network didn't learn anything about the image. He went to look at, okay, excellent. I learned the label and that's it. So it did its job greatly, but clearly, you need to be careful with this. That's why when I say first of all, understand your data, clean your data, and so on. Then there are other problems that, of course, can still happen. But I think like motion can fake lesions, stuff like this. You can simulate this in adversarial way and force your network to ignore artifacts due to not useful information. You can use uncertainty to estimate how reliable is a prediction, and then focus only on these adversarial tasks. So, okay, I know these regions are more critical because I never seen this in my training. So let's the network dig more into that aspect. So it's as well as the other topics is ongoing research. There are tools you can use, and it's getting better and better with time. And we know the mistakes that we do, and we learn from them.
I react to the example Luca made about a cable detached or a part of the detector which is not functioning for some reason or broken. I will answer, this is why we have a simulation of our detector. Because we want to model every possible effect, even after the detector has a failure. You can reproduce this failure in the simulation, and the simulation helps you to understand why, where, when there was the failing. Then you can modify your simulation in order to reproduce the failing and train the algorithm on a failed detector, for example. But this would not answer to the question how you discover that your detector is failing. Of course, you can discover it by comparing Monte Carlo expectation with your detector signal. For example, you get half of the energy every time respect to what you get from Monte Carlo, and you do not understand why. And then you start to check your detector. Even if it's on a satellite, there are some way to check it is functioning. But still, I think that I agree with Marco that it is an open problem. Then if you have a bug in your training data set or in your data acquisition after you do not know where it is, it will completely fool your prediction or your understanding on the prediction. I think this is a really important problem. And maybe the art of a scientist, the art of a physicist can help to focus on the problem, to spot the problem.
It's really cool indeed. It's a good question, and actually you gave me an idea to how to to tackle a problem that I was dealing with. So just by discussing, thanks a lot. But totally, I mean, it would be great actually. And so as I was saying, we can use all the tools that are already there, I mean, for anomaly detection, but also, yeah, I never thought that GANs can be used to inject systematic errors and actually it would be cool to inject them and then without being aware of that, so that you are able to test if you are able to detect anything. And so you gave me an idea. Thanks a lot. I mean, that's, I think, was one of the aims of this workshop, I would say. Yeah, it's cool.
Okay, thank you all the speakers for the great answers. Okay.
So since we are a bit late, let me ask one last general question that actually is kind of 3-in-1, but try to not go too far. So I would like to ask all the speakers to comment what is their idea of the role now of deep learning in the scientific method. So what they think is the best application of deep learning in the scientific method. And if you were to suggest to someone who is young, so a PhD student, master student, young postdoc who is interested to look into this, where would you tell them to start from? So what are some perhaps new interesting techniques or some knowledge that you think would really help? And perhaps those things we could collect at the end also. Giuseppe already put something in his slide, so that was very helpful. Please.
I just can quickly answer on that. I would say that deep machine learning, it's a new powerful statistical tool. I would say it's like when you learn to do statistics, right, to analyze your data, and I would say that this is gonna be another tool. Maybe it's I'm reducing a bit the power of that, but the way I'm using it, it's like another statistical tool. I mean, to analyze my data, the data that I'm dealing with. So yeah, in the scientific method, I would say that in the structure that Galileo proposed, I would say that it doesn't change that much. I would say that the scheme is always there, but then we have another tool like fitting, an extra tool. How, from where to start from? I would say that there are online courses, but I would start from. So all of the, I mean, so there's the supervised, unsupervised. Now maybe the distinction is not anymore. I would say that you need a basic course to familiarize with, and then follow your gut feeling. But it's really something that is mandatory in these days. I mean, to keep engaging in the discussion, in the scientific discussion.
Marco, Francesco, any comment?
Yeah, I can add, always in the scientific method, I think it's a really valuable tool for hypothesis testing and to identify the correct question to answer to that your experiment can answer. Like the example I gave you before, they were questioning what's the contrast in the brain. The machine said, listen, there's a label, tells you straight away if it is diseased or healthy. So you should ask yourself, what else? Or what's the relevant information, the whole image, the metadata are maybe more insightful. And hypothesis testing, they are great tools, statistical tools, like Giuseppe said, because they enable you to really tackle complex combination, manifold of parameters you want to test with your theory. And often it's impossible to do. So the scientific method starts with hypothesis that simplifies to the essence a phenomenon, because we cannot account for everything. Well, machine learning can help you include more hypotheses, and then let the machine decide which one were redundant, which one are not useful. So what we do now, because our cognitive ability is limited, we a priori, make some assumptions which are reasonable, but they are not generalizable to any kind of system. So maybe that can be a direction. But for the time being, machine learning is not artificial intelligence. That's the point. At the moment, machine learning is a statistical tool. It's very efficient. By that, it cannot invent, it cannot propose new things at the moment. That's the direction where artificial intelligence will go one day. At the moment, we are at the beginning. I'm confident we will reach that self-aware, self-learning machines. So an example of that is the AlphaGo that Giuseppe mentioned before. From the first release, the DeepMind just released a few weeks ago, the very last version of AlphaGo, where they also optimized the architecture to play the Atari game. Now, conversely to Go has rules. So you teach the machine learns the rules, and then it uses those rules as they want, okay? But you give them the rules. So they are not inventing anything. They are not going in the scientific method. They are not proposing hypotheses. They are just, you give the hypothesis, they just give you the most efficient solution. In the last release, Atari doesn't have rules. So the machine learns new hypotheses, how to play more the game in a more inventive way, if we wish. And that's kind of amazing, I think. It's really amazing because it learned a way that is not encoded, and it came up with that, which is promising, I think.
So they actually trained on all the interesting answers to the question. But I mean, for what concerns me, I agree with both of them. To me, they are really powerful tools to perform tasks, as also Marco underlined, to choose between hypotheses, statistical hypotheses. And if I have to advise a student or a person that wants to know something about it, is that, I mean, there's a lot of interesting theory which I'm still studying, still trying to understand the math behind it. And if you want an overview, there are interesting books you can have. One was also quoted today, Machine Learning by Young Goodfellow. It is a good book to have an overview. I mean, it is not comprehensive, but still, you cannot have the full picture after one book. And in my experience, I also learned a lot about the theory beyond the algorithms, the way they work, hands-on. I mean, I have a problem. I want to find a good answer to this problem. I start to document. I read. I try algorithms. I try how they work, and this is a good practice, I think, in this field, because this field is not static at all. It's always developing very, very fast, and you really have to keep updated because after 1 year you can you realize to use a tool that is outdated, really outdated. A student comes to you and tells you, "This is outdated. I did it. I studied in the books. Now this is how it is done." And I mean, there are good reviews of hands-on courses and methods. I think that one of the best I found is a book of Jason Bell, which is called Machine Learning Hands-on for Developers and Technical Professionals. It looks a bit specific towards application and not towards theory. But as I say to you, I mean, this is if you want to learn, you have to do a lot of practical work, a lot of trials, and if I have to think a way in which I insert deep learning and machine learning in the scientific method, it will be like the instrument of the scientist right now, as it was before a fit tool like Minuit. Minuit was the algorithm for the fit. Now we have a different one. We have Adagrad as statistical stochastic gradient descent. And now it is a tool to prove statistical hypotheses. And really interesting one in which you cannot launch the program and be sure 100% that it converges. But you have to be creative, find a way how to solve the problem.
So if I can add one more suggestion, is about the fact that because these tools are developed by a large community, basically, even proper companies put out there their TensorFlow, their PyTorch, you know, they are really willing to push their branding, which is good, is excellent. You find out on GitHub loads of architecture already there. Now, the problem is you may start just downloading scikit-learn and using the fully connected neural network that it's already there. It's a function, and you just start there. I would recommend to start trying to implement your own fully connected network in your own language, Python, MATLAB, C, whatever. Try with a simple 3 multi-layer, fully connected layer. You have your nodes, your neurons, because only in that way you understand how it works. Of course, for more complex, like convolutional neural network, I don't recommend. I recommend to use PyTorch, TensorFlow, these packages. These are excellent. But like Francesco said, hands-on, also starting from the basics. Try to implement your own architecture from the basic, and then move higher. And there are loads of online courses from MIT, Stanford. They are excellent. They are free. You can just follow them, and they really give you a lot of insight on to start. Then everything is just try and share. Also, sharing is very useful. If you put out on GitHub your architecture, you can also receive feedback on how to improve it, you know? So sharing is really essential in this moment. And we have all the tools to share everything, so we should.
Thank you very much. I would like actually to add just a very last remark on things that someone should focus on, since it's outside of physics and people do not consider it often, which is a bit of computer science itself. So how to structure your data analysis pipeline, your machine learning pipeline, which seems something trivial. It is not, absolutely. And learning how to do that properly will save you from a lot of errors, the worst of which is data leakage, where basically you are a hypothesis entering the test and pollute the only sample of data you have to evaluate how good your method is. For this, you can look at, well, if you look around for data science pipeline, data science templates, etc., you will find a lot of stuff which is shared freely. There are articles on archive, there is really everything. But really also take some course on programming, how to structure a code. That helps a lot. Okay, I would like to thank again all the speakers and the organizers for this wonderful afternoon, for this occasion, and all the attendees also for staying with us till now. It's quite late. And with this, I will also like to leave the stage to the organizers themselves for the final remarks.
Yes, okay. So we hope that you enjoyed the meeting. So we have. So a special thanks to all our panelists. So to Luca, of course, for moderating the whole event. And of course to Francesco, Marco, and Giuseppe for their precious works and talks and propitious discussions, I think. And then I want to thank also behind the scene Andrea Di Luca, which helped us for the technical direction of the webinar. And I just want to say that the next Young Researcher meeting will be probably online, but when it will be possible, we are waiting for you at the University of Trento, so here in Trento. However, you can find all the details of upcoming events and so on in the IPN International Physicists Network website. Then you can find us also on social networks like Twitter, Facebook, LinkedIn, and also on YouTube, where you can find also the registration of today's event. And then also if you want to join the community for organizing events or other things, just contact us. I think that's it. So thank you for your participation and have a good night or whatever it is in your time zone. Bye.
Thank you, Marta. Thank you, the organization.
Thank you.
Thank you so much. It was amazing.
Thank
Have
you,
a
guys.
lovely day.
Bye.
Bye-bye.
Thank you all.
Bye.
Bye bye.